future. Okay, so who's got an answer? Who can tell me what a rational number is?
A ratio? Or like being a ratio?
Okay.
Any number that can be written as a fraction.
Okay, so any number that can be written as a fraction. Ratio, fraction, same thing. Did anybody have a more detailed definition than that? That was it? A number that you can write as a fraction. Okay. So then what's a rational function? What's the difference? Okay, so again, you're basically working with an equation now that has x's, but you're still dealing with some kind of a fraction. So like 2 over x. There's an x involved this time. Okay. All right, question number 3. This is a biggie for today. What is the parent function of a rational function? What is it? Good. Okay, so did everybody come up with this? F of x is equal to 1 over x. Okay, and what does it look like if you graph it in your calculator? Like what?
It's like that.
Ooh. We should like come up with a name for this. Kind of looks like that, right? What do you guys think that looks like? What? Like, are you kind of saying that there's some symmetricalisms to it? Some symmetry, that's a better word. Yeah, it's definitely symmetrical. So like, did anybody notice that this is symmetrical over this like invisible line that goes directly diagonal, like the y equals x line? Anybody notice that? That's an important thing to observe. Okay, so in the past, since you guys didn't come up with a cool name, I'll tell you my name. Because I generally have pretty cool names. Tilt your head slightly to the side. See the hourglass?
Oh, yeah.
A little bit. So that's what I call this one. So just as a descriptive name, I'm going to call this the hourglass. Does that work? We're on the same page? Okay. Cool. Okay. So what we're going to do is we're going to talk about rational equations and very basic ones at that. So everybody's in OneNote, yes? Okay. So this is what we're going to do. We're going to work with Desmos a little bit today. So what I'm going to do is I'm going to go ahead and in your so everybody go to the content library, go to module 8. And 8.1 specifically. It might take a second for the link that I just put in there to appear. Tell me if you're not following along with me. Everybody sees what I see? They're already synced? Oh, you don't have the module 8? Okay, so do you have a little green thingy right here? So like what you can do to force the sync is if you push your stylus on the advanced math and pull off. The first option on the top is sync this notebook, so force it into sync. Is it going to sync or do we have other problems? Because that's a possibility. Sometimes it'll require a login. Everybody's good? Okay, so everybody sees exactly what I have on my computer screen. Okay, so what we're going to do is I'm going to have you copy and paste this page into yours so that you can write on it, and then we're going to do some of the examples together, so we'll take a look at what you're doing. So this is how you copy and paste a page into yours. Are you ready? Stylus in hand. Ooh, good. Good form, everyone. Okay, so we're going to hold our stylus on the 8.1 page, and it's going to make a little square, and you pull off. Okay, then we're going to copy that page, and then we're going to go to our folder. So hit the little green arrow, and Emily's gone today, so I'll be Emily. Okay, so you should be able to see your name right here. I have to go down to find Emily. There we go. Okay, and we're just going to do in-class notes. We'll just put it in the in-class notes folder. Okay, so this is a blank page. We're going to insert this page here. So again, hold your stylus right here on the blue until it makes a square, and then paste. Okay, and now you should be able to write on this page if you so desire. Pretty good? Okay. I also want you to go ahead and click on the Desmos link because we are going to use Desmos to kind of investigate our rational equations. So everybody click that link and it should automatically pop open a browser for you. I have like 89 different ones open. Okay. So the first thing I want you to do in Desmos, so now everybody's in Desmos, yes? Check, check, check. Desmos? No?
I don't know.
Okay.
There you go. Yo. Stop.
So you guys tell the number 24.
It was in the one for 20.
Oh, we have on 3 tabs.
Oh, it's okay. What did you get that one? Look at you investigating. All right, so has everybody typed in 1 over x yet? 1 divided by x. Okay. So the cool thing about Desmos is it allows us to zoom in and out really easily. Okay, and that's going to be super valuable because there's kind of things going on with this function that are very unique. Okay. So first thing I notice, or actually I'm not going to notice it. How about you guys explain? What do you notice about this that is kind of unusual to anything we've graphed so far? Okay, let's raise our hand. I heard like 3 people talk. Okay, Sean, hit it. Oh. Okay, so neither of those 2 pieces touch the axes. Super important point to make. What else do we notice? There are like 2 pieces. This is the first time where we have a function that actually splits apart and kind of exists in 2 different areas. Does anybody else notice anything besides those 2 kind of details? What? Wait, say that again, but I think yes. Say that again, but I want to make sure I'm on the same page. Y equals negative x. Oh, so this line right here, y equals negative x?
Yeah.
They're a reflection, like a mirror image? Ooh, good observation. Yeah. And they're also reflected over the y equals x. So symmetrical in 2 different aspects. Good. I wouldn't have noticed that other way. Interesting. Okay, so let's talk about what Sean said first, because it's a really important thing that is happening. Okay, if you zoom, okay, let's start way over here. Where do you think that this function is going? So as x goes to infinity, so if we go really, really, really far to the right, that's pretty far, don't you agree? And I push on a point way over here, and I'm actually going to zoom in because I don't like the number that it's telling me. Still not doing good. I'm going to zoom into this. There we go. Oh, that's good. I love Desmos. Look at that. Okay, so the bigger the x gets, what's happening to the y value? It's getting smaller. Smaller, 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 smaller. Okay, so think of what's happening in this. Like, we're dividing by x. So let's pretend, for example, that x was 2. Okay, so let's say I have this amount in my hands. And I take it and I divide by 2. Okay, so I cut it in half. And then I cut it in half again. And then I cut it in half again. Cut it in half again. Cut it in half again. Basically, what you need to realize is that we always have something that we just keep cutting in half. Okay? So what's happening is we are getting infinitely close to 0, but never actually reaching it. Okay? So I'm going to introduce a new number to you. Okay? So, by the way, notes. Make sure that you are taking notes still, even though we're using the tablets. Remember, you can't use a tablet on your test or quiz. Okay, so write down some of this. This section particularly is called Graphing Simple Rational Functions. Okay. So just so you know, the essential question today is basically we are going to be graphing these rational equations in this form specifically. Does anybody notice that form specifically? Like there's like H's and K's, it's vertex form. Okay, we have worked with this form before. We used it when we were graphing polynomial equations. So we are going to use this exact form with rational equations. That same idea of if we add something to the outside, it still moves it up. If I add or subtract inside to the parentheses, it moves it left or right. Okay, the a value in the front basically affects the slope. We'll talk more about that b value. Basically, we're going to kind of kill that idea and just rewrite it so we have an a value. So probably pieces you would want to write down in your notes. Oops, that was a really bad circle. Let's try that again. I would write that down in your notes. And I would also make sure to graph the parent function. Okay, and we'll talk about that parent function.
So the only difference between the vertex form is that it's over 1. Or 1.
Yeah, 1 is in the top. Yep. Yep, it's just written as a rational function as opposed to a polynomial. Okay. Can I scooch? I'm scooching over. Okay, so I'm not going to follow what the textbook does. We're going to kind of investigate this in our own way, if that's okay with you guys. So we're talking about our parent function initially, 1 over x. Okay, so if you graph the parent function, we'll just draw this in your notes so you have it. You see the hourglass. Okay, so we just talked about the end behavior. Okay, as x goes to infinity, what is the y value approaching? 0. Okay, so for the end behavior, we can say end behavior as x approaches positive infinity, our y, or in this case, I call this a g of x. What is our g of x approaching? 0. Okay, what about in the negative direction? As x approaches negative infinity, what is my y value approaching? Also 0. Okay, so this is kind of a cool thing. Okay, what is happening is there's a horizontal asymptote. Shall I write that word down? Hold on, I spelled that wrong. There we go. Okay, horizontal asymptote. Okay, so anybody dare to take a guess at what an asymptote is? Okay, I'll give you a hint. So this particular one, what? Did somebody make a funny guess? No?
I have no idea. Yeah,
Okay,
oh, yeah.
so think about what is happening over here. Okay, this function is getting really close to the value of 0. Okay, so we happen to have a horizontal asymptote on this graph at y equals 0. Okay, if I was going to graph the line y equals 0, what would it look like? It's just the x-axis, right? So it's like this invisible line right on the x-axis. Okay, so the asymptote is this invisible line that the function is getting infinitely close to, but it never actually touches. Okay, so that by definition is what an asymptote is. It is an invisible line that the function gets infinitely close to, but never touches. Do you want me to say that again for people who are writing that down? Okay, it's an invisible line that the function gets infinitely close to, but never reaches. Okay, so we have this horizontal asymptote going on. I'll wait for you guys to stop writing.
The function gets
Infinitely close to, but never reaches. It's kind of like an invisible barrier. I don't know, I just thought of like Star Wars all of a sudden. It's like a fence that's invisible. Okay, so does anybody notice anything else that's happening with our graph? Like what Sean made that statement about? There is such thing as a vertical asymptote. Want to make an educated guess as where one might exist on this?
X equals 0.
Yeah, exactly. So there's also a vertical asymptote. And specifically at, what did you say the equation was? X equals 0. Okay, so do realize vertical lines, this is review, right? Vertical lines are always x equals, horizontal or y equals. Okay, so if I was to use my Desmos and kind of look really close at what's happening as we get closer and closer to the x value of 0, the function is going to get infinitely close. Why?
Is that fun in y?
Huh?
Without a fun for y?
No, but good one. Why would it get so close to 0, but never touch it? Why can it not be 0?
Oh, because you can't divide by 0.
Say that again.
You can't divide by 0.
Because you can't divide by 0. The math god said, thou shalt not divide by 0. Okay, we got an x in the bottom, so that creates this vertical asymptote that splits the function apart. Okay, simply because you cannot divide by 0. Okay, yes.
I just have an unrelated question, but is there a difference between x and like infinity? I wonder if it's like, x.
What do you mean by that?
Well, x could be anything. You can say, x could be 0, any negative number, any positive number, whatever you want it to be. Is there a difference between that and like infinity, so to speak?
Well, they're completely different ideas. So x is representing the idea that the value of x can be any number. whereas infinity is technically a number that exists far, far away
Alright.
and is a large amount of somethings. Okay, so what we're going to do is we're going to take this whole idea and we're going to do the translations with it. Okay, so we're just going to graph this, okay, using the same idea as we did with the polynomials before. Okay, so on your guys' OneNote, I want you to go down until we get to the assignment part. Takes a little bit of scrolling. It's really far down. Don't worry, we're not going to go over all that stuff. Woo! Finally found it. Ooh, that was hard. Okay, so eventually way down at the bottom, get to the part where it says homework and practice. Okay, so we're going to start with a couple of these, and then we're going to go straight through the graphing because this part is incredibly simple, I would say. If I was going to ask you about number 1, okay, so it says simply describe what has happened. If I have a +4 at the end of the function, what has happened? Up. Okay, perfect. So you would say, oh, this went up 4 units.
Oh, describe.
Yeah. Okay, and if we were going to do number 2, you would say, okay, so the 5 basically does this slope change. And to be very precise about the slope change, we want to say that this would be actually a vertical stretch of 5.
Or back.
Back at those, we sure are. Okay, and for number 3, if I have a +3 down underneath with the x, it would go to the left 3 units. Ooh, here we go. It's getting harder. Number 4. Two answers would work for this. Okay, let's stop for a second. Okay, so you wrote this down over here, right? Let's take a brief moment to evaluate what we're talking about. So we have the A, and then we had 1 over B x minus h plus k, right? Okay, so let's quickly talk about what all these things do. Okay, we just talked about the k. What does the k do? Up and down, right? So to be very precise, we would say up is if it's a positive k, down would be a negative k. What about the h? Left and right. If I go left, what kind of value do we have? Positive. And if I go right, it would be a negative, right? It's like opposite inside the parentheses, right? Everybody follow that? Okay. Let's talk about the A. Just talked about the A. What does the A do? Way out front. Okay. So it affects the slope directly. Okay. So I'm going to say that we're going to use this idea of slope because in my opinion, it makes things so much easier. Okay. So we're going to use this idea of slope. If it's on the outside like that, it's a vertical. Okay. So we can have a vertical stretch or we can have a vertical compression. Okay. How do we make a stretch? It's greater than 1. So if my A is greater than 1, it will stretch. How do I compress? Yeah. So we'd rate that it's got to be between 0 and 1. So 0 is less than A is less than 1. Okay, let's talk about the B. This is the most complicated idea in my opinion. Okay, so the B is the horizontal stretch and compression. We can still think of it in terms of slope. In fact, I'm going to still write the word slope because I'm going to show you how to rewrite stuff so that the B becomes the A. Okay, but just so you know, how do you make a horizontal stretch? What kind of value would we have for the B? So here's a hint. When you do things vertically, up, downs, it's always like what your brain thinks. So what I mean by that is, our up and down, positive went up, negative went down. When we had the A out front, the bigger the A was, the further it stretched. Okay? But when you do things horizontally, it's like opposite of what your brain thinks. Okay? When we had a positive, it actually moved in a negative direction. And vice versa. So, how would this slope idea work horizontally?
So greater than 0, less than 1.
Exactly. Very good.
So A would be K and B would be H.
In that sense, yes. Okay, so compression basically kind of is like the reverted of our vertical idea. B is greater than 1. Okay. So, now that you have that idea, we can think of this as two ways. Okay, so would everybody agree that this would be the same as 1 over 0.1 times 1 over x?
Sure.
And if you have 0.1 written as a fraction, what is 0.1 as a fraction? 1/10, which I like fractions way better. Because look at this. Look at how much simpler this is. Because if you divide by a fraction, that's the same as multiplying by the reciprocal. So this is actually 10 times 1 over, whoa, wow, that was intense. Okay, let's try that again. 1 over x. So therefore, what could we conclude about that? I got a big fat 10 out front. Vertical stretch. Vertical stretch. And that's where I'm going to leave it today, instead of talking about horizontal stuffs. That's okay with you guys. If you want to play the horizontal game, feel free. You value your brain cells. Good. Okay. All right, so we pretty much hit all the pieces there. That was pretty simple. Okay, so let's now take this translation and let's graph it. Okay, so we're going to do this first one together. We're going to break it down. I'm going to tell you exactly what things I'm going to expect from you. Okay, so, and I want you to kind of ignore what this says up here for a second. We will talk about it later. Okay. All right, first of all, tell me the translations, the easy parts. If I have a -2 at the end, what direction does it take us? Down 2. Okay, so we know this is going to go down 2. And then I have a +1 inside the parentheses, which takes us to the left 1. And then I have that big 3 that's in the front, so that's my vertical stretch. And I'm going to go ahead and say m is equal to 3. I'm going to play the idea like it's a slope, but you guys understand that it's not literally a slope, right? It's not a continuous slope. We're just using it to come up with reference points. Okay. All right, here comes the part. I'm not going to use their graph because, I don't know, I guess I'm used to drawing my own. Here we go. Okay, so there's my x and y axes. Okay. So the first thing that I'm going to draw are my asymptotes, okay? And I want you to represent asymptotes with little dotted lines, okay? So let's talk about, let's see, we did down 2 first, okay? So which asymptote would that affect if I go down 2 units? Okay, so yeah, It affects the horizontal one. So think about this. If I had a vertical asymptote going infinitely up and infinitely down. If I go down 2 units, is it going to change my vertical asymptote at all? No, it's exactly the same line. But if I move it to the left or to the right, does it change? Then it changes. Okay? Horizontally, what kind of movement affects my horizontal asymptote? Up and down movements. Okay? So, let's go down 2. So I'm going to draw down 2, and I'm going to represent it with little dotted lines. Okay? So that's how I expect you to draw your asymptotes. Okay? And then what I'm going to do is I'm going to specifically label that asymptote. So what asymptote did I literally just draw? It is a horizontal asymptote at y equals -2. Perfect. Okay, so I expect for you to state that. Okay, now let's draw the left 2 movement. Okay, so I'm simply going to move that to the left 2. I mean, I keep saying, well, I wrote 1. Minor details. You guys are following me. Okay, so I move it to the left 1. So what asymptote did I just draw for that one? Vertical. So I'd say I have a vertical asymptote at x equals -1. Perfect. Everybody good so far? Okay. So now here comes the part where I have to come up with some points. Okay? And depending on my particular equation, I can come up with more points than others. Okay? So what is my, and I quote this, vertex -1, -2. So my vertex, and why would I quote vertex? Because it's not on my function. My function does not go through -1, -2. Okay, but I'm using that vertex to come up with my points. Okay, so from my vertex, I'm going to plot my slope, which is 3. Okay, so my slope, by the way, is 3/1. All agreed there? Okay, so from the vertex, I'm going to go up 3 and over 1. Okay, so up 3, 1, 2, 3, over 1. Where do I land? Okay, so I want you to label that 0, 1. Okay, how else could I come up with a reference point? Okay, good. I can go down 3, 1, 2, 3, and over 1. So what is this point down here? -2, -5? Yeah. Okay. Now I want you to type this into Desmos, and I want to see if you can come up with another point. Okay, or maybe more than one other point. Okay, so come back over here in Desmos. Okay, so we had 3 parentheses 1 over x minus 1. And then make sure you get arrow over so you're outside the parentheses after you do that. -2. Okay. +1? Oh, sorry, I wrote the wrong equation. Thank you. That would be helpful. So the other thing that I can do, and just so you guys can see this, I can actually graph in my asymptotes if that helps you to visualize what you have on your piece of paper. So we had one at y equals -2, and this is really cool about Desmos. Okay, you can do that. And you can also graph vertical lines on Desmos, which you cannot do on a calculator. X equals -1. Okay, so now we can see that vertex. Can somebody see an additional point that we have not listed yet?
just basically making the hourglass transition from the original.
Yeah, moving the hourglass. Yep, exactly. What? 0.5. Oh. So you found x and y intercepts. Okay. Is there a way that we could easily come up with the 0.50? I mean, it's an x-intercept, so we could say the easiest way to do that is set the y equal to 0 and solve it. I'm not going to make you do that. At least not this time. Did anybody else notice a nice, beautiful point that it crossed? Yeah, like this one right here. You see that one? How do you get to this point? From the vertex. What's the translation or the movement? Up 1 over 3. Does that sound familiar at all? Like, what was our slope? Up 3 over 1. But we went up 1 over 3. Yeah. Like, literally just flip them. And the reason that works, one, 2, 3. So that was at 2, -1, right? Okay, the reason that works is because our function is symmetrical over the y equals x long, which is also kind of moves with our vertex. Okay, so what would this other point over here in this little quadrant be? So if I went down 3 over 1 to get this one, what would my other movement be? Down 1 over 1. So I could go down 1 and then to the left 3, and that should be a point on there, and you can check that with Desmos to make sure. So how about that one looks like 1, 2, is that -4? Is that -3? You guys agree with that? Wow, I totally drew that in the wrong spot. How about that? Okay, so once you have those 4 points, you can draw your hourglass. Okay, remember that you cannot cross those asymptotes. Awesome. Okay. Can I go to the next one? Okay, so I'm going to have you do this one. I'm going to start this one with you because I don't like the way it is initially written. Okay, so I'm going to rewrite it with you, and then I'm going to have you graph it. Okay, so right away I notice there's a 0.5 in the bottom, which I just hate that. And I really hate the way that the book throws this in here, because by definition, if any of you guys would have actually looked up the definition of a rational number, it's a number that you write as a fraction, but it has to have whole numbers as the top and bottom values. You cannot have a decimal within a fraction. That is improper. Okay, so if I was going to rewrite 1.5, that's the same as what? 1/2. So this is like -1/2 right here. And technically, if I am dividing by -1/2, what's that the same as? Multiplying by 2. Okay, so the function that you're going to be graphing is -2 times 1 over x minus 3 plus 1. Okay, so what I want for you to do is on your tablets, on this page, okay, I want you to do this. Okay, I'm going to give you a second. I want you to make sure you label your asymptotes. And I want you to come up with 4 reference points. If you want to start by figuring out what are the movements, that's where I would start. It goes up 1, goes to the right 3. That makes it very simple to come up with your asymptotes. And just so you guys know, I'm going to watch somebody. No pressure though. Anybody want to volunteer for me to watch them? So I'll just pick somebody randomly. Perfect, Jacob. He's got this.
Shut up. That's enough. It's like 2 bits.
Where did you put this? Oh, there it is. Couldn't even find it. Did everybody notice that the slope was negative? Did everybody notice that the slope is negative? So what does that do to a function? Flips it over the x, so it flips it upside down. So be aware of that. It looks a little bit different. Picking you next time. Are you done?
No, I keep checking when we calculate.
Oh, every time you.
Yeah.
Every time you like hit it or what?
Well, every time I go over there,
Weird. You must be hitting something. Have you added points on here?
no,
Is it the OneNote or the Desmos that's not working? Oh. Can you do it without Desmos? See if you can do it without Desmos. Go back to your OneNote and see if you can use your slope, because you have a good start. You just need some points now, and just use your slope to get there. Ooh, there we go. Nice. Okay. So, what do people think about Jake's graph? So he's got the points 1, 2, and 2, 3 up there, kind of in the top left area quadrant. And then down on the bottom right, 5, 0, and 4, -1. Did anybody concur with the way Jacob did this? Does anybody disagree and say, wait, I got a different point than that? Everybody all got the exact same 4 points? Does anybody have a question about where these points came from? Okay, Jake, would you mind explaining where these points came from?
Well, I just got it.
You just got them from Desmos? Okay. Can somebody else come up or explain where these points came from? Someone who did not use Desmos to find the points. Go ahead.
I just kind of kept plugging in up there, so got some.
Ah, okay. Interesting tactic, because I never said that. So you just picked X values, plugged them into the equation, and came up with corresponding Y values. And you got still the same exact numbers?
Took a couple tries, yeah.
Took a couple tries. Interesting.
I just
It's
didn't
nice
find
there were
out,
whole
like,
numbers.
two, whole numbers that I.
Yeah. Yeah, you kind of got lucky on this one being whole numbers. So that was kind of nice. Okay. Anybody else? Everybody did exactly that. You picked X values and plugged them in.
No.
What'd you do, Erin?
So like you make the things, I don't know.
The asymptotes?
Yeah.
Uh-huh.
Those, and then where they cross the vertex, and then you use the slope to get 2 points, and then you flip the slope and get 2 more points.
Okay. So the place where they cross is right here at 3, 1, which we're calling the vertex. Okay. Quoted vertex. Okay. So from here, then what did you do, Erin?
Then I use -2/1.
-2/1, the slope.
Get 2 points.
Okay, so what are the directions you did? From here. Down 1 over 2. Okay, so see how this comes from? Down 1 over 2. Whoops. Okay, so that gave us 5, 0. And then you also went up 1 over 2. So that's where 1, 2 came from. Okay, and then you also did down 2 over 1, down 2 over 1, and up 2. Okay, so using the idea of slope. Does that make sense, this idea of slope from the vertex? Okay. Okay, let's try the next one. Okay, so again, I'm going to help you rewrite the next question, because again, they give you this nasty decimal, which I don't like. Oh, that started me way up there. Huh. That was weird. I lost all my stuff. Maybe I was writing in the wrong one before. Anyways, okay, so number 11, how would I rewrite the 1/2? Or, I mean, the points half. Okay, good. So negative 1/2 is going to be your a value, and then you have 1 over x minus 1 minus 2. Okay, graph this one. I will tell you this is tricky. Tricky, tricky. Oh, this is not tricky. Except for there's a small trick. There's one detail you must pay attention to. Should I? No. Next time. And just so you know, you might want to double check your points on Desmos on this one. Ooh, you redrew them. Whoa. Are you accidentally hitting your, you must be accidentally hitting your keyboard. Okay, so while Jaden is perfecting this, the points that she has drawn, although she hasn't labeled them yet, do we agree with these points or not? Can you guys see them? Yeah, I'll try to zoom in a little bit more. Do you agree with those points? Okay, because she initially had different points, which maybe you might agree with those instead. But what? You know they're wrong. They are wrong. Do you know why they're wrong? Okay, so should be done? Okay. So this is correct. The ones that Jaden has here, I'm guessing is going to pop out a beautiful little hourglass in Christmas colors. Sometime today. There it is. Good. Okay, so the slope of this one is -1/2, which is kind of tricky to think about. Okay, so when we analyze the slope of our polynomials, do you guys all remember this only works if you're one horizontal unit away from your vertex? One horizontal unit away. Which if I rewrote this slope would be the same as 1/2 over 1. So -1/2 over 1. So this is basically your up and down movement, and you always go to the right or to the left 1 for this slope. Okay, so if we're at our vertex, everybody okay with the vertex being 1, -2? Everybody nailed that part? Okay, so from here, if I go down 1/2 and over 1, I land at this point right here. Okay, so that point is exactly 2 and -2.5. Okay, I can also flip that fraction because of this function's symmetry, and I can go down 1 and to the right 1/2. Down 1 and to the right 1/2. So that gives me the 1.5 -3. Okay, and we can do the same thing into this other direction. So I can go to the left 1 and up 1/2. So that point is 0, -1.5. Okay, yeah, there's an negative. And then this one would be up 1 and over 0.5. So that's 0.5 -1. Okay. So everybody recall that little fact? That the one horizontal distance. Okay. So are we doing okay with graphing? Do you feel pretty confident in it? We don't need to keep doing more examples? Okay. One thing that they do, okay, is they write the function in a different form. Okay, so they give you this this other form, which would be like a standard form, and they take it out of our vertex form. Okay, so what I want to do is I want to show you how to put it into the vertex form so you can graph it. Okay, so write this example down in your notes. You're going to want this one. Okay, so in order to rewrite it, what we're going to do is we are going to use long division. Okay, so this idea of long division is going to be helpful in more than one place. Okay, so to do this, I'm going to have my x minus 1 as my divisor out front, and then the 3x minus 5 is the dividend that we put inside the box. Okay, so doing long division, I look at the x and compare it to the 3x, and what do I have to multiply x by to make it 3x? 3. So the 3 goes upstairs, and I multiply that through. So what is 3 times the x? 3x. And what is 3 times negative 1? And then what do I do? Subtract. Here comes the hard parts. Okay, so our x's go away. What's my constant number? What's negative 5 minus negative 3? Negative 2, very good. Okay, so what is negative 2, by the way? It is my remainder. Okay, so my remainder I write as plus negative 2 over the divisor. Okay, now this kind of starts to become our vertex form. Do you see it? See it? Okay, now what I'm going to do is I'm going to rewrite it in the correct order so it looks just like this. Okay, are you ready? The number that's on the top is a what? Okay, yeah.
Like which
Yeah.
form you
Which
mean?
letter is it in our vertex form? It's our a value. Okay, so this is going to be negative 2, 1 over x minus 1. And then my 3 is a positive number, right? So I say plus 3. So this is now the equation that I would graph. Okay, so I'm going to finish doing this problem completely because the one thing that I haven't talked about yet is the domain and range inequality notation, all that stuff. So to just quickly do that, I'm going to graph it so you can analyze it very quickly. Okay, what are my two translations here? So the plus 3, okay, so plus 3, I'm going to take my vertical asymptote and go up 3. Okay, so I have a horizontal, well, that was a terrible H. Horizontal asymptote at, what's the equation? Good, y equals 3. Okay, I also have a movement to the right 1. Okay, so this one is a vertical asymptote at x equals 1. Perfect. Okay, if I wanted to quickly input my points, I have a slope of negative 2. Okay, so from my vertex, I could go down 2 over 1, land right here. I can also go down 1 over 2, land right here, and do the same in the opposite direction. So without labeling those points to waste time, I'm just going to draw this really quickly. Okay, so now, let's finish doing this part right here. Domain. Who remembers what domain is? The x values. Okay, so from your left to your right, what is the domain of this function? Okay, so what's the one value that x cannot be?
No, wait,
1, right? It's the one value that makes the denominator 0. You can even use the initial equation to see that. Okay, so my domain cannot equal 1. Okay, now this says write this in inequality set and interval notation. Okay, so let's just write it in interval notation. Okay, let's kill that. We don't need to restate all the obvious. Let's just do interval notation. Okay, so this is the one you see most often anyways. Okay, so interval notation is from the smallest to the biggest. So what is the smallest value that x could possibly be? Negative infinity. And then it goes to 1. And do we include the value of 1? It does not. So we use a parenthesis. And then it starts over at 1 to positive infinity. So there's your domain. The range. The range is your y values, okay? So your up and down values. What's the one value that the y cannot be? 3. So in our case, the y will never be 3. So how would you state that in interval notation? Negative infinity to 3, not including 3, and 3 to infinity. Fair enough? Done. Check.